So our last bit on bivariate data for year 11 is making predictions. This is our whole point of what we've done through bivariate data. It's being able to find an equation so that we can predict what will probably happen in the future. There's two ways to make predictions. We're either going from the graph or we're going to do it from the equation. If we're going from the graph, we're going to rule a line from the axis to where you are. Now, I can't use a ruler with this thing, so it's going to be as close as I can possibly get it. But you rule a line from the axes to the line of best fit, rule down or across to the other axis to find your predicted value. So the following graph is going to show drink sales and temperature for a 2-week period for a local pool canteen. Predict the number of sales for a 20-degree day. So we find out where a 20-degree day is here, 20 degrees is there, and I'm going to get it as close to a straight line as I can. We end up there, and we end up going across. And if I notice where the line was, it's just above the 100, but not by much. So again, a ruler would be by far your best way to do it. And I'm going to say we go in over to 101. So I went up to the line, then from the line across, and I end up over here at 101. So we predict 101 sales. Predict the temperature required to sell 120 drinks. So drink sales is here, 120 is on this line. So again, we get out a ruler, and that's not what I want to do. Get out a ruler and go across. That's a long way off a straight line, but you can see the line I'm trying to keep to. From here, then go down until you meet your thing. If that's 24, that's 26. We're going to say 27 degrees is our thing from our graph. Now, ruler makes it a lot more accurate, but we've still got, with this number, do we know if that was 101, 102, 101.5? We're not 100% certain. So we have got the ability to predict from the equation. Now, I've already done the regression line on this and ended up with drink sales equals this temperature. And we're going to predict the number of sales for a 20-degree day. So our drink sales, or we can write it as sales, is 46.15 plus 2.73 by temperature. The temperature was 20. We're going to put that into a calculator and see what our predicted number of sales was. And when we put that equation into the calculator, we get 100.75. Very close to 101 we predicted from the graph. Predict the temperature required to sell 120 drinks. The sales is now 120, so in place of sales, we write 120 equals to, the equation was 46.15 plus 2.73 by temp. Now, we can either backtrack or you can use nsolve. Either way, we've got an unknown here. You have to find out what that unknown is. And whichever method I chose to use to find t, I end up with 27.05. So these two answers match very closely to the 27 and the 101 that we found from the graph. So the question has to be, why do we need to know both? Which one do we use? Yes, predicting from the equation will be more accurate, but if you were given this graph which looks like this particular one over here, is there any point in finding these exact dots when you may get them slightly wrong and then putting them into an equation? Right? If you got a graph, predict it from the graph. If you've got an equation, predict it from the equation. Pretty simple way to go through it. A couple of things that we need to talk about also is a definition of interpolation and extrapolation. So going to just draw a quick idea of a graph here. We're going to call this height, and we're going to call this age. Hopefully it looks a bit more like age. And we'll say 2, 4, 6, 8, 10. I'm not even going to put a scale on here. We're going to say our dots are going to be something like this. So as someone's getting older, they're generally getting taller. If we need to make a prediction and we got our line of best fit can fit through the middle, if we want to predict for someone who is 8 years old, if we come up from the 8 years old, it fits within our data. Our smallest result was 2, our highest result was 10, 8 is within that, it is interpolation. If it's from outside the data, and now our line of best fit at the moment looks something, and that again would be ruled, something like that. If we wanted to predict for a 50-year-old, we're predicting over here somewhere. It's outside of the data that we're giving. This thing is what we call extrapolation. Now we're going to talk about why that can be an issue in a moment, but the reason I've used height and age is when you hit, say, 16, 18, 20, whenever it happens to be, if we continue this line on, it's going to stop being a linear equation. This is an issue with extrapolation, is we don't know if this relationship is going to stay the same. So for a prediction to be reliable, and I'm going to just get rid of this piece that I've written on here. For a prediction to be reliable, there's two major things we're going to look for, and then there is a third one that helps as well. If it's got a strong correlation, so an R value close to 1 or -1, then it will probably be a reliable prediction because it means that we've got a strong positive or negative correlation. The stronger correlation, the more reliable your prediction will be. The prediction must be interpolation to be reliable. This is because, as we just showed with that height and age, the relationship may change as extrapolation is used, and therefore the answer you get may not be quite as reliable. And our third one is the more data points you've got, the more reliable it will be. Because if you've got more data points and it's still got a strong correlation, it means that that is definitely going to be more realistic. Interpretation of the line of best fit, or the regression line. What I've got is just use height and age again, because what we'll talk about there. We've got height in centimeters is -25 plus 2.5 times age. It's about knowing what this number at the front and what this number in front of the age is. Hopefully we remember the number in front of the age is the gradient. What the gradient tells us is how much we expect the response variable to go up by for every increase in the response variable is over here, if I want to point at the right spot, for every increase in one of the explanatory variable. So taking this and putting it into the words that you would have to write, it's expected that someone grows 2.5 centimeters every year. Or you could say it's expected that someone grows by 2.5 centimeters in 1 year. If this was a negative 3.2 or something, you would say that it goes down by 3.2 for every 1 year. The other thing we've got is the number by itself, which is our y-intercept. The y-intercept tells us what the response variable will be at 0 in the explanatory variable. So in this particular case, it's expected that at birth or at age 0, that someone will be -25 centimeters tall. Because this -25 centimeters doesn't make sense, people are not going to be a negative height. Just say that this is unrealistic due to it being a negative number.